We're going to spend some time setting this up, hopefully around 20 seconds, and then we will start. So I'm super happy to be here. The reason being, the title starts with computational design. So, yes, exactly. So the funny thing is, my colleague, let's start this. It's kind of like giving me a lot of energy, has been in it for a long time too. So I stepped on the US soil 20 years ago to do my degree master's degree at MIT in computational design. And for 2 decades, my affiliations and jobs have been about explaining what computational design is. And on the side, I also tried to do, some projects. As we were discussing with Duan for this conference, I didn't know that I was going to go first, but I submitted the title, Design Computation Human. And then, I tried to kind of like bring computation back to being human and, reveal what computers cannot do as a computational designer, so I can use my computational strengths to do the best I can. So that's my approach. It's slightly different. Sometimes it causes troubles for me, but, I go with that. So my question when I came to MIT was, okay, how can a computer render this, right? So that was my question. Computational aesthetics, I like the image, but can I teach the computer to render that? So today, I just type it. This is a AI-generated image. So you just give the prompt, it creates it for you. But if you go back 19 years, that was kind of like rough, and I didn't know much about it. I was an architect, by the way. My background, I was an architect, but I'm not a programmer. So what I realized was, okay, there's a meaning that you understand in products, in vision, but also there's the information that I have to kind of like deal with all the time, right? So if I have to quantify anything, I have to go into it, look at it, understand it, and then subdivide it into like little components, and then so you can combine them back and make something out of it. Actually, help the machine make something out of that, unlike me, because I don't have to kind of like subdivide the world into pieces while I'm looking at it. I understand there's a room here, I see you, and so on and so forth. So there's a really great article about it, this subject of meaning and information by David Bohm. If you're interested, just check that out. David Bohm is a famous physicist who passed away quite a while ago. So what I did was, at the time, I'm like, okay, let me take this picture. So I heard about this thing which is called gray levels, right? So you can do some bitmap processing, and I was like, okay, I can try that. Let me learn a little bit of like programming for that. So I thought myself, programming in Max, 3D Max script. And I started analyzing the images in 3D Max, right? So I was plotting let's say I was segregating the darks and brighter pixels. I was trying to also look into composition of the images. And then I was trying to do some like edge detection, which I learned from, a friend at electronics department. I was like, okay, to detect objects in the scene. So he was like, okay, there's this algorithm which helps you differentiate between determine the shorelines, as you're kind of like from the satellite pictures. So I was like, okay, let me try that. And then I made another algorithm. I made it up. I was like, okay, if I go from left to right, how much the grays are changing, like brightness is changing from left to right, and I plotted them. I combined the three, algorithms. I set some scores. I sorted them. I let the computer render images. They were like 32 pixels to 16 pixels overnight. Okay, and the next day I went and found the selected images and re-rendered them in a large format. And then I prepared this UI, to let's say set your rules for rendering and so on and so forth. And then I realized, wow, that was a thesis on computational aesthetics that I did. I had no idea. And I also didn't know that it was about machine learning, because it was image processing, feature detection, segmentation, fitness scoring, and so on and so forth, right? So then I started seeing these people like AI experts, prompt engineers, kind of coming forward and front and talking about, yeah, Midjourney is amazing, and so on. I was like, okay, well, maybe I have to think about it a little more. So I have this 10 years between my master's thesis and the PhD thesis. So in between, I got really intrigued about like what computers cannot do, as I was explaining. And I went back to MIT and I was like, okay, I'm going to do a super blind system. I don't want the computer to be smart. I just want it to help me replicate myself. And I I started drawing these on diagrams. So if you look at that on diagram, which is kind of like open, it's not like a flow chart because I had problems with like inputs and outputs. In my mind, everything was flying in the air, so I was trying to represent that. So what's happening here is that there's a transparent surface. You make watercolor drawings, and then you can actually capture whatever you draw, and then you can project back to your drawing underneath, and then you can trace your own, trace. So like tracing your own trace. So, and I can talk about it in mathematical terms. So if you look at the schemas at the bottom, you see x goes to t of x, so something is being translated on the surface. 0 goes to x is like nothing, goes to something, and you can get. What is interesting in this kind of computation is that it's open-ended because you end up like creating some weird stuff. Let's say the red circles, which weren't inherent in the system. They weren't there, right? So the human perception is interesting in the way that you can just kind of like make things up, right? But unlike a data set. We will discuss about that later. But at the same time, I was super interested in like keeping the material qualities, the things we touch, the things we interact with, right? So painting is really important in that aspect. Like as a designer, as an architect, as a kind of like hobbyist painter, I was really interested in not being able to touch the stuff that I was designing all the time. But also, like I think my point was, okay, these things don't have to be that far apart. If you know about shape grammars, actually you can make these kind of visual computing and then translation of in terms of mathematics, right? So it's like or rules that x goes to x plus translation of x goes to x plus part of x and so on. So the difference here is that I'm not multiplying or adding up numbers like 1, 2, 3, right, which are super abstract. I have shapes, and shapes are my units. And a shape doesn't have a definition. It's just a weird stroke, and it doesn't have to be definitive, so it can change over time. So it's a pretty interesting way to compute, actually. So if you want to kind of learn about it, you can read about this book, which is What Computers Still Cannot Do, which was published in, I think, like 80s or 90s. So this is already like 3 decades old, and there's the first version of this book, which is quite interesting. So I finished the PhD. I got, I'm like, okay, I'm still having this ambivalent feeling against computers. By the way, I'm really using them, right? So I don't have anything against computers. I love it. I'm a computational designer. I make my life with it. I sleep with it. I wake up with it, and so on and so forth. But I started doing these oil paintings and taking the pictures of them. That's exactly when the style GAN started emerging, right? So people were kind of like collecting these data sets. For me, it was a retrospective thing because I had the data set already. It was my interest that kind of like captures this picture and just put them together. And then I trained a custom model on this, and I got these images which were, okay, I'm like, interesting, but what are they? They're not exactly my paintings. And it was interesting to see the reflection of the patterns from the paintings, but at the same time, the patterns from the photography. Like you can see depth of field, light blurs, and also those kind of like visual qualities in these images. So then I did this. There's sound. I don't know if you can play it, but not a big deal. Okay, so it's fine. Anyway, so there's music. It's not a big deal. What's happening is that's the latent space of paintings that are trained by like the ML machine learning, the trained model. And then I took them and I exploited them in space, and then I added these like tectonic levels, because I'm an architect and lost painter, and then I'm designing shoes at the same time. So this was kind of like confusing to me, but I like playing, and I was like, okay, what am I doing really? People ask me when I show these, they're like, what is the purpose of this? Like, why do you do that, right? So I was like, okay, I was just cloud gazing, right? Like looking at the clouds and trying to see shapes. And this kind of like connects with, so Solnit says, okay, why am I doing this? So you need some sort of something to be efficient, purposeful, and utilitarian in the modern world. And if it doesn't work, if you cannot measure it, there's no meaning into it, right? So like how can we kind of like get away from that? Because I benefited actually from these kind of like cloud gazing stuff a lot. So anyway, that was the critique, I think, of the book, and I kind of like brought it back here. And then, of course, this kind of like play, do we do that at work? Of course we do. And again, more than 3 years ago, we looked into, some SGAN models, and we were like style GAN models, and we were like, okay, what if we trained something on speed that would inspire designers to use these things for, making sketches and and creating concepts. And I wanted to move forward, like push it forward a little more than that, and recruited some of my friends and said, hey, are you on board to create something that we can showcase, we can kind of like demonstrate in the company? That's my take usually. When we come up with ideas, I have to do the proof of concept and just push for those things. This is, I haven't seen this in person because I was away. Still, I haven't seen it. I'm back to US, but this was 3D printed. Somebody, I really don't remember who did it actually. Put this sock like an upper in it and then sent the picture, photographed to me. I'm like, oh, okay, like this is really doable. Can you wear it? Yes. Can you run it? No, because it's not the right material to do that, right? So it's just visual. But it's okay to make these kind of like, again, like cloud gazing kind of stuff. So these are some crops from the concepts that we built on the office. So just to show that, okay, we can push the digital stuff like crazy, right? And especially if you're not manufacturing or printing them, right? So there are no limits. So on the mathematical side, on the formula side, we show that. Well, is that useful? Actually, turned out to be because in corporate class in 2020 at MIT, which was bringing this, like super crazy concepts and the knowledge that we developed at New Balance by 3D printing. I'm going to give a break here, and this event is great. This is the second note about it. One was computational design. The other one is I already met some people that I have met digitally, but I've never seen them physically, right? So I saw those people, and then I also had friends who were, that I haven't seen for like 15, 20 years. They are here too, and then this class actually became, a conversation, online conversation with some people, and I saw some of them here too. So with that, again, like thank you for, letting me talk about this material today. So if we go back and okay, we have the crazy digital stuff, we have the manufacturing. So how do we kind of combine these things? And design is about kind of coming up with the problems that we can really restrict and find answers for. So motorcycle riding is an interesting thing. It has nothing to do with bicycle riding or driving, if you ask me. And then your body position counts a lot because similar to any sports you do, right? So your kind of ergonomics are really important because you can do something wrong and things can go really wrong. Or the material itself is designed for a specific purpose. So if you want to go fast, it looks different. The way you hold the handlebars, where you put where the pegs are, how you sit, and you see some people kind of going like this on the road, right? So just kind of borrowing that idea as we were getting ready for this conference, I asked in the group, can we do something similar for running to explain it to people? Because I learned when I started working for New Balance, I knew nothing about shoes except wearing them. I can do my laces too. But then I said, okay, what if we explain the the ergonomics in terms of cushioning, which changes tremendously depending on the activity, the drop that you have in the shoes, and put all those together to show that, okay, it's really kind of like the motorcycle design, where things go is changing depending on the purpose. But at the same time, just to represent that it's so hard to design shoes. Like, how can you, because shoes are made by using lasts, which is the internal mold, right? You build around. So you're seeing the section of the, the last. But you see the foot. The foot has not, there are connections between the foot, last, and the shoe. But, computationally, it's, I would say, almost impossible to define, right? So there's a guy who knows last, and he takes it, and he's like, he does this, and he's like, oh, I have to shave it a little bit here. That's it. That's his knowledge, and I don't know how that information will be kind of transferred to the next generation of last makers. So that's designing for, right? And then we design with. So this is an interesting subject because data, it has been hot. It's super hot now because of 3D printing, AI, and so on. So data is an interesting thing. So here is data, for instance, by an interpretation of data by Tim Noll. So Tim Tim knows, he's kind of like attaching these pens to trees, and the wind is blowing. So the tree is plotting something, making art, right? But at the same time, it's the data that's representing the stiffness of the branch, and then the magnitude of the wind, and so on and so forth, right? So depending on that, actually, that data is something that we make, right? So I can say, hey, data is exactly the thing that is found under your feet as you're walking or running. So I can just say that, right? So you can say, okay, data is this, data is that. And then where it comes from is actually, it comes from wherever you look at for finding it, okay? So as an architect, we looked on the surface of buildings for making solar simulations, or to make the, structural analysis of the buildings to look for that. So data is exactly at the location that you're looking at. So here is an insert, pressure insert that you put in your shoe, and once you start running, let's say we can measure the event, the pressure event that happens as you're running from the kind of like landing and takeoff. And now what you do is, okay, there are numbers, let's split them, let's record these numbers, let's parse them, let's write a code, and then let's just make sure.
Let's make a design space, let's let structure on the design space.
Now let's just make sure that our structure looks good. Let's make sure it's connected, it doesn't break apart. Let's make sure it's kind of carrying, it's doing what it's supposed to do. Let's explore some different options. Let's look at the softer ones, harder ones, and then let's print them so we can have a better understanding. Because if you stay in the digital, well, it's not tangible. If you're wearing something, you have to feel it. If you are feeling something, it has to be sturdy, and it has to have a lifetime lifespan, and it has to perform. So we ended up doing maybe 1,400 parts so far, but for a specific study for these shoes, triple cell technology, we called it, we created two shoes. One had this forefoot part, the other one had a heel part. It was a really interesting process of kind of like creating, learning, designing. And the goal was, okay, let's design these two shoes, which are, by using the same material, which are behaving significantly different than each other, and let's put these parts in different locations in the shoe. One is a forefoot part, the other one is a heel part. And then let's show that, okay, we can customize things if needed, and by using the same material. So that's a learning from design for additive manufacturing, right? So I'm taking you from computational aesthetics to drawing, to paintings, to building making, which I didn't show, and then to DFAM. So what's happening in DFAM is there's a big shift in, parts are changing, processes, methods, and tests are all changing. And this is just to acknowledge that, okay, the material is the same, but you can do a lot by using the same material and same process and make the thing perform really differently. And this also being in footwear business, so what I learned a lot is actually footwear design empowered me to use the claim. So I always said, okay, simulation is not reality, it's not gonna work. I always give the example of Bank of America building in Manhattan by, like Times Square, which was a, LEED platinum building. There's an article about it, you should read it. Simulations were a huge percentage off. What is important here is that what you see on the 997 shoe, the colorful one, you see ANCAP reveal. So there are nested components in there, let's say 5, 6 parts, nested together, which are, together doing something for the shoe to perform. Whereas in the black one, you have one single part, which is by lattice design, doing all those things together, no nesting, nothing. You just print it and it works. This is also bringing the notion of how we understand the world, right? So you can represent and describe a shoe in very different ways. In my mind, it's always this like blue, yellow, green thing, because it's like very mushy. That's how I feel with my, feet in it. So like all the other representations are not that accurate. But also the parts are, by nature, they are just scientifically put there because, again, it's like data, because we want to understand and talk about it. Can anybody tell where your finger ends and your palm starts? Well, there's a line there, but it's not, if you scale in, there's no line, actually. Everything is connected, right? Same thing for trees. We cannot talk about trees, so we have to kind of like subdivide it into pieces. Same for engines, right? So here are different piston representations for you. They're like totally different. Depending on what you're trying to say about engines and pistons, because it can also become an artwork, right? So this is there are lots of pistons there, and they're just being used for the sake of making an artwork. Okay, so this is a scientific method, pretty much. Our assignment is for science, for building, is to go to the landscape, go to the beach, and then we are asked to take a handful of grains and we need to sort them into categories, right? So as we start categorizing parts with our scientific knife, right, we split everything into, let's say, buckets, depending on the color, size, translucency, transparency, and so on. But then you pick a grain, and then it doesn't fit into any of these clusters. What do you need to do? You either need to go back and change your classification, or you need to kind of cheat a little bit and just kind of, ignore that grain. So this is from the book that you have just seen. It's from the Zen and the Art of Motorcycle Maintenance by Robert Pirsig, talking about the scientific method. Okay, we're coming to the end. Okay, what do we learn by working with computers? One, ambiguity is really important. So if I ask you if the point is inside or outside in the condition A or B, you would say like that. You know which one is inside, which one is outside. Counting the number of intersections. So you would see that if the number of intersections is odd, the point is inside. If it is even, it's outside. Beautiful. We took something perceptual and solved it computationally, but the problem is we lost the curves, right? So look, we lost the vision. That's very important. When we say, for instance, computer vision, or artificial intelligence, it has the vision, but the vision is super different than ours. Same thing for artificial intelligence, which is totally different than our understanding and learning processes. So for design, you also have to come up with these binary things work for a while until you find the crocodile, which is super important to say. Beyond the duck and rabbit, you have to search for this to add real value. And speaking about values, it's really important because this is from Albert Dürer from 1514. So he said, what is beautiful? I do not know. In the picture, you see tools of computation and measurement, pretty like the hourglass and the compass and the, the hammer. So today we're okay, what can I do with ChatGPT and Midjourney today? I don't know, before I go to bed. So you are kind of constantly being bombarded with these tools, but, where's the meaning in using those? So you have to be critical to find that. I took this class from Patrick Winston at MIT, and I happened to, as a designer, read all the papers from 1952 till our day on seminal papers on AI, which helped me a lot to understand how AI works, which is also helping me, comment on AI and so on. But beyond it, I think collaboration is really important. We're really at the end here. So I have the New Balance design team with me at this conference because we said, okay, we're going to go and learn a lot in the conference. So these are actually combining all this knowledge of sculpting, but at the same time, bringing data, bringing, let's say, performance to shoemaking. This is all done by the computational design team at work. But then also what we do is to kind of connect everything. We are okay, let's bring the new tools. We have the data, we have machine learning. Let's be inspirational. We are designers. Let's keep everything, and then do something with it. And again, put the proof of concept on the table. So this is pretty much that. And I said, okay, it was a month ago. This is the end. Thank you very much. A month ago, I said, okay, why are we trying to constantly make shoes by knitting? Because the patterns are so interesting, and shoes are too small. So I said, make a sweater. And I said, if you make it, I'm going to wear it. So now I have to fulfill my promise right here. So this is the first data-driven, machine learning made sweatshirt that was done actually completed one day before we drove here as a team. So I would like to thank the computational design team at New Balance. They will be around in this event, but we are missing our knit expert who is in another team. To combine everything. But again, we just kind of create stuff and put it on the table to see if there's any value or not. Thank you.